Thanks so much, everyone, for coming to the forum. My name is Mirella Tulbur. I'm a faculty here with the center. And first of all, I'd like to thank everyone for making this happen. So first of all, Dr. Mintemeyer, the director of the center, John Vogler, who's done a lot of the work, Rachel, and Mary Hicks. And I'm delighted to host our today's speaker, Dr. Matt Hanson. Matt is a professor of geography, or in the Department of Geography at University of Maryland College Park. He's a remote sensing scientist, and he's the lead of the Global Land Analysis and Discovery Laboratory, so the GLAD team. And GLAD investigates methods, causes, and impacts of global land surface change using Earth observation data as the major data source. Matt's work as part of NASA's MODIS land science team included the algorithmic development and product delivery of the MODIS vegetation continuous field. And then he was among the first remote sensing scientists to take the entire Landsat archive and map deforestation in the tropical areas, and then take up that method and work in their seminal science paper, High Resolution Global Maps of 21st Century Forest Cover Change, which was published in 2013 in Science, and I think lots of us have used that data set. Matt is currently on the Landsat science team, and he's definitely one of the biggest names in large area terrestrial remote sensing, and has influenced the field and lots of scientists, myself included. Prior to joining UMD, Matt was the founding director of the Geospatial Center of Excellence at South Dakota State University, which was the R&D kind of branch of USGS Aeros Data Center. During his tenure there, in a short amount of time, the center became one of the best in remote sensing in the world, so I think in top 5 or top 10 globally. And I guess on a personal note, I just want to say that Matt is one of those people that can switch from chatting up people at Kinshasa in DR Congo in Kikongo or Lingala local language, which he learned during his time as a Peace Corps volunteer, to filming with Harrison Ford on why Earth matters to NASA. So please join me in welcoming Matt.
Thanks, Mirella. Thank you. All right, thank you all. Thanks, Mirella, for the introduction. So I'm going to just talk about our work with large area mapping and monitoring. The basic idea is the satellite has this consistent calibration, and when it's over the Amazon basin or the Congo basin or Borneo, we're getting the same response. So if we have a good input, a consistent radiometric input that is enabled by the satellite, we can apply an algorithm and map consistently some theme. Could be primary rainforest, could be rice cover, surface water dynamics, what Mirella does, and have really consistent apples-to-apples comparisons across large areas through time. And to date, in historical terms, the way we do global assessments of our natural resources is countries submit their area of forest to the FAO, and then we glue this stuff together. And countries have very different definitions of what a forest is. In Namibia, the forestry department is not, Congolese will not consider anything in Namibia a forest. Just doesn't, it's not included in their definition. So you have this problem of really where are we in terms of the state of our resource, how they're changing, and what the human factor is in terms of those conversions and modifications of the land surface. So that's the whole deal. So all this stuff is at scale. I'm going to go through some examples and kind of like our general strategy. Just to kind of reflect upon the geospatial sciences, and I think you guys get this, I think by nature we're interdisciplinary. You know, people who do our work are good programmers, they're good statisticians, mathematicians, they know how algorithms work, but they also know geography, they know the environment and how it changes over time, the distributions of things, pattern recognition. So they have a really good basis on the dynamics out there in the world and what's going on where. Drivers and the like. Also just in terms of our particular thing, remote sensing, how to calibrate and process, you know, digital image processing. So it's a lot of skills, and if you have all the skills, you're killing it, right? Not everybody has them. Some have 2 out of, you know, 2/3 of them. Some have 1. Maybe that could be enough if you're doing, you know, maybe machine learning, convolution neural nets. Maybe that's just enough. But I think the real strength is if you are competent in multiple of these, you put them together, you can pose the question because you know the environment and what's happening, and you can answer the question because you have the tools and the methods and what's appropriate to answer that question. So It's kind of neat like that, I think. We're very international. Our group is, Russia, Congo, New Zealand, Bolivia, Pakistan, which is really fun. And we do have, I'd say a third of our work is working with capacity building. That's just a backdrop. We do work with different countries on their forest monitoring and agricultural monitoring capabilities. And that's where I just came from in the Democratic Republic of Congo, working with their forest inventory group. I just want to mention that because we do a lot of outreach in that regard to port our capabilities to operational settings. And now I'll get on with it. So our first product that was global in nature is 1994, published in the International Journal of Remote Sensing. It's a 1 degree by 1 degree spatial resolution land cover map. You can almost color it by hand. And this pixels are 111 kilometers on a side at the equator. And this made peer review. We're still really proud of this map. Had room for improvement. I'm going to show you kind of a bit of our evolution. I'm going to zoom into a pixel of mixed forest in Arkansas. It's pretty cool. And this was made possible because NASA wanted to have some vegetation maps, land cover maps to parameterize the general circulation model. So we were working with a biospheric modeling group at NASA Goddard Space Flight Center, and scientists over there went from 1 degree down to 8 kilometer. It's called the Pathfinder data set. Had about 17 years initially of this and these are from AVHRR. One of the cool innovations of the team at Maryland at Goddard was to use meteorological data to map the land surface. So figuring out methods to get rid of the atmosphere, all the weather, we're all about looking at the atmosphere. This was like, how do we process these weather satellite data to look at the land surface? And they figured out some methods to do that. And then there was a 1 kilometer version. Now we're seeing some kind of pattern in the landscape. You see settlements and the like. And then there was the MODIS instrument launched in 1999. And it had 7 land bands. So these were spectral bandwidths that were designed to avoid all of the problems with the atmosphere. So go through these little atmospheric windows where you wouldn't have scattering due to water vapor and the like. And we could map at that. And that's not a great map, I'll be honest. I don't like that map. But anyway, this is a 250 meter map. It was, MODIS has 500 meter and 250 meter bands. 250 meters, pretty cool for looking at some of the bigger land changes. Some of the big agro-industrial clearings in the tropics, for example, or fires in the boreal. Pretty nice. But what's the longest living satellite, Earth observation satellite record is what series of satellites? It's an easy question. Yeah, sorry. Sorry to ask such a dumb question. Landsat, and Landsat's launched in 71, 72, at the time of the blue marble picture from Apollo 17. It's weird that we've had that kind of capability up in space for that long. But the problem was the data were not usable with our computing. We could not process the digital data. The way we mapped with Landsat back in the day, does anybody know? Yeah, we drew on glossy photo prints. The biggest photo lab in America was at Eros in South Dakota, and they'd send these tubes with a rolled up image, and you get a light table and you draw on a GIS. And you still have, Indonesia still draws on their heads-up GIS on a computer, but they still do this interpretation on a fixed enhancement of an image. But that's the way we did it, because we didn't have the computing. Of course, in the 90s and 2000s, we get high-performance computing going on. Now the cloud is there. That's solved. Great. The other thing that was limiting about Landsat was it wasn't globally acquired. It was kind of hit and miss. A lot of agriculture areas, but no systematic thinking about the planet until 1999 when they launched Landsat 7, and there was a seasonal acquisition strategy globally. So only in 1999 do we have something approaching a global record. So check that box in 1999. The biggest problem was the cost. You had to pay for it because it was jointly run with NASA and USGS. USGS put a cost model on it. And everybody, Tom Love and other folks that worked with these data said, we use the data we can afford, not the data we need. The nice thing about that is you could get a PhD with one image. It's pretty cool. I got a master's with the one image. I bought it for $250. I got a master's degree. Great. Super cool. Now if I read a paper and it doesn't have like 10,000 images, I'm like, get out of here, whatever. It's like. But the point is they made it free in 2008. And it was cool. I mean, the story about how it becomes free is really neat, but they pushed USGS. And USGS has done a few studies repeatedly to show that the value added, the use of the data, pays for the mission, right? And that's like a piece of infrastructure. It's a piece of, it's a public good piece of Earth observation infrastructure. And those analyses that show that it pays for the mission are just on U.S. use. We don't care how much value it is made outside of our border, but everybody, a lot of people, Europe mapped all of their baseline land cover and land use with Landsat data. And even Brazil, even though they have their own mission, they map the deforestation in the Amazon with Landsat. So that's pretty cool. So I'm wasting time on that. This is what this place looks like with Landsat. And again, this was made possible in 2008 when they opened up the archive. And we could take all of our algorithms that we'd run on these big blurry pixels and run them on these pixels. So we didn't really innovate so much, but we just did the same thing. Our initial one was run with Google offline, really. We didn't develop it with Google Earth Engine. It wasn't ready for that. We had a great interrelationship with the team at Google Earth Engine, and they ran it once, and there was a bug, ran it again, twice, and it was done. That's still the map that's up online. But we had the code, and it was just to turn it into JavaScript and string it across the 10,000 CPUs or whatever they have there. But the interesting thing, obviously, is when you get down to 30-meter resolution, you see the bottom line hardwood forest is the kind of landscape you might have around here with the Roanoke Tar rivers. And then the uplands are largely forestry. So if you look at the change over time, practically all the upland forests turn over in about a 20-year period. So that's pretty cool. So now we have this spatial detail that allows us to track really a lot of the major and most common frequent land dynamics. And we can do it at scale. I show this, this is just to show that the time series is the deal. We started with AVHR and MODIS, which are daily polar orbiting large swath sensors. This is MODIS, and we now working with Landsat. So I'm waiting for it to start acquiring data here, but they're polar orbiters, sun synchronous, and you have to deal big time with the clouds, right? So we process every pixel in the MODIS archive, every pixel in the Landsat archive. The first thing we do is QA. We got to throw away all the data that are cloudy, hazy, shadowed, whatever. So we do a lot of work both QAing and radiometrically normalizing the data. I'll get back to that in a second. So in this graphic, it's basically saying that our heritage instruments were these coarse spatial resolution, daily, high-frequency imaging satellites. And then when you get to Landsat, a single Landsat is every 8 days. If you put two together, kind of a virtual constellation, you get, every 16 days, you get 8 days with two of them. And we really want to be down here. So this is like high-res daily, right? But with Landsat, we're up here. If you talk about a single free-flying digital globe satellite like QuickBird, it could be 2 months or so in terms of their nadir repeat coverage. But there's a commercial company right now, Planet, that has hundreds of small sats up, and they're putting those in a constellation, and they're getting 3-meter near daily. That's pretty cool. That's where we want to be. High spatial detail, high cadence. When we take Landsat 7 and 8 and we combine them with the European instruments, which are Landsat-like, the Sentinel-2 series, and there are 2 of those up right now, we could have 4 satellites working together. These are 10 and 20-meter land bands plus the 30-meter. We can have a really cool capability that approaches, a planet, but it's not there. And all I want to point out here is that this box right here, right now, is commercial. So if we're going to do global mapping or large area mapping, it doesn't work buying data. You can't do it. So this has always been our problem. We work with the free, public good kind of infrastructure. I'll show you some examples of this, but the idea that we could work with this at scale is it's a non-starter just because of the data volumes and the cost, primarily the cost. Okay, so this is just a recap. We have, great computing, we have great algorithms, we've got global data, and we have a free and open data policy for things like Landsat and Sentinel-2, so we're on our way. To show Landsat over time, and this is just the TM series starting in '84, you can see our volumes increase over time. In 1999, that's where the global strategy started with Landsat 7. Not so great, but when we get Landsat 7 and 8 working together, this is the last 5 years, the first time we have just kind of like a flat, repeated, dependable volume. It's very hard to create a turnkey algorithm if your data volumes change dramatically, right? If you run the algorithm that works in 2018 back in 1995, it's not going to be working so well. So this is really a problem for kind of building a history of the planet. But right now we've got this nice, steady capability. Hopefully we can work with this for a while. And the plan is to, Landsat 9 is going up a year from now, and I don't think we'll backslide, hopefully. So we start off with an example of scene acquisitions that aren't radiometrically corrected. We have to normalize, take out the angular anisotropy. We have to do a lot of pre-processing, and we can take these kind of raw data and turn them into clean, seamless images of the planet, and then through time track phenology, track change, land change and the like, and turn that into a product like this, which is tree cover in green, tree cover loss in red, tree cover gain in blue. Where you have both loss and gain, it's pink. That's the southeast US. It's a big tree farm. IKEA from space. The blues here are the biggest, that's the biggest gains. Those are Soviet collective farms in the ex-Soviet Union being abandoned. But you really see kind of, land use and all the fire, it's just kind of a clean map. And again, 30-meter spatial resolution. The holy grail is to say we have a globally consistent, locally relevant product. We're not always locally relevant. We have error, right? And we know where our worst parts are. Cloudy areas like the coastal Gabon. We know where we have problems with our data. But there you go. This is the conversion into a thematic map. And then we can look at dynamics over time. So we can say, okay, what are the trends in disturbance in forest over time? And this color bar is saying, when it's yellow, it's early. When it's red, it's more recent. And if you look at the tropics, there's a lot of warm tones, oranges and reds, except for the arc of deforestation in Brazil over this period. And that's really cool. When Brazil did their interdiction to slow deforestation, the satellite portrayed the scale of the problem. They had a high of almost 30,000 square kilometers of deforestation in 2004. They put together a policy. They empowered their environment agency to not just to make the policy, but to enforce it and arrest people who were illegally deforesting. And they brought down their deforestation rate to 4,000 square kilometers by 2010. This yellow color is showing that. That's the proof of that policy interdiction. And we know from this past summer that there's a lot of backsliding. This backsliding has been going on for like 5 years. From the low of 4,000, around 5,000 kept, and now they're going to push 10,000 this year. So the idea, what's interesting about, I think, the environment and conservation movement is you have to win every battle forever. And they did a great job. And I still, when we're talking about success in slowing deforestation, they're the champs. They're the only one who did it. And they did it dramatically, but they didn't sustain it. And you can just, we can talk about why, but they've gutted the power of their environment agency. They've removed their indigenous people, the indigenous agency enforcement out of the protected areas for the indigenous people. So they've backtracked dramatically. But anyway, that's a pretty neat piece of evidence. So I'm going to talk about different applications and how we do our work. I'll start with just the mapping. We work a lot on the pre-processing of the imagery to make these clean time series and to derive statistical metrics of them. We know what metrics drive different land cover and land use themes in terms of mapping. Ours is all supervised machine learning stuff. We work a lot on training data. So training data is where a lot of domain expertise comes in. If you're going to train a crop type map, you got to know all the crop types. You got to know what their distributions are. You have to be able to train all this variation in spectral space and thematic space to kind of make the algorithm relate to these data very well. Our algorithms are decision trees. We bag them. We are working with computer vision methods with deep learning, but our workhorse to date has been these decision tree algorithms. And then you get a map. And once you have the map, there's this loop mainly through training data, but we can loop through here too. But this is like the active learning process where, when you make your first iteration, you're up here in terms of error. With 2 or 3 iterations, you do dramatic advances, and then there's this long tail where you're just trying to hammer out a few last issues, but it's just your expertise, right? You are doing this process. And at some point, you got to give up the OCD and let it go. And it's very important that the map is not, we know a priori the map's not perfect. So our final map will have errors. And one of the things that, well, I'll get to this in a second, but the map is not the thing that policy is wanting, because the map doesn't have the statistical properties that policy demands. I'll get that. So we need to report 10,000 square kilometers of deforestation in Brazil, plus or minus some uncertainty. And the maps don't have any uncertainty, and they're inevitably biased. So we can't do that with the map. I'll come back to that in a second. So this is the way we approach our mapping. At the top we have really land cover, so vegetation form, vegetation presence, absence, and we can scale these things globally pretty easily, but when we get down in the blue, we're talking more about the land uses. We might have natural forest versus forestry versus trees associated with shifting cultivation. So we've got this really more complicated stuff, harder to map. A lot of what we can map, mapping's easier higher up in this archive, in this hierarchy, and sampling is better for characterizing some of these more thematically challenging themes. So here's where I'm going to add to the method. So when we do mapping, this is the first block, we get a map. The map, we think in our head is a stratifier. So we can map deforestation versus everything else, or we can map urbanization versus everything else. And we can throw samples in those strata, and that's our second step. And this is according to answer the guidelines of UNFCCC protocols. So IPCC demands that you use unbiased estimators to do your area estimation with an associated uncertainty. Again, the map doesn't give you that. But if you do samples and you look at reference data can be in the field. They can be other sources of data, like high-res shots of imagery that are very clean and easy to interpret. With those samples, we can get an area. And so this is what we want to report to conventions, not the pixel counts. So we do samples. And once we get the area out of this step, we can go back to the map. And we can fix the map, in a sense. We can make it unbiased, at least. So this is a third of our work is this, a third of our work is this, and a third of it is, the capacity building side. 10 years ago, all we did was this, and we were so happy. It was just great. Just make a map, kick it out the door. Say the accuracy is 85%. Yay, we're good, right? Policymaker doesn't know what to do with 85%. That doesn't make sense. They want to know that it's 10,000 square kilometers, right? They need an area, plus or minus. So this is very, 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 very important idea. So the samples, traditionally in remote sensing, give you an accuracy. Of course they do. That's fine. But the first thing we do is we take the area estimates from them. This is from Mark Broich's paper, Morales' husband. This is nice, but this is going back a bit. This was our first paper, I think, to show that the satellite was a great targeting mechanism. So if you're going to do land area estimates, you could just throw random samples or systematic samples. But most of the time, we're interested in change, and change is often a minority, a very small fraction of a landscape. The satellite tells us where change is occurring. So if we're looking in Brazil and we can stratify and throw a bunch of samples in where we're mapping change, we get very low uncertainty. So the map is our targeting mechanism for any of our land dynamics. And we will get a factor of 10 times the efficiency from a stratified random sample versus a simple random sample. So this is really the huge benefit of the satellite. Hope that's clear. If you have any questions, just stop me, no problems. So I'm going to show a first example, and this example is for the blue category here. We have trees in red, other vegetation in green, and blue is bare ground. I'm going to make it brown now. So this is just bare ground. This is very high in the hierarchy. Very simple to map non-vegetated land. Pretty clean. We map time series of this, and we say, where are there permanent conversions of vegetation to non-vegetation? And we can make a map of that. Nobody's waiting for that map. I've got a bare ground gain map for you. I don't care. But we can make a map of that and throw samples in there and talk about, okay, what's the rate of urbanization? Because that's usually associated with devegetation. What's the rate of energy or infrastructure development or energy extraction, resource mining, that sort of thing? It's tiny. It's a tiny area. But if we do this map very well, we can target it. So here's an example of what this looks like for Dallas-Fort Worth. In blue are bare ground gain pixels for two different periods, but we see an airport extension, we see a highway, We see all this kind of commercial development around the airports. Airports are the CBDs of today. You build an airport, the city grows to the airport. And we can say, now I can throw a bunch of samples in this blue colors and a bunch of samples outside and really target that dynamic and assess what's going on in this way. This is what the map looks like at scale. You can see Beijing, Shanghai. This is North Korea. It's very quiet. This is not night lights, right? It's a different thing. It's bare ground gain. We can see other different resource extraction activities. I'll show the U.S. All these light blues are fracking. Anybody know what this stuff is? Mountaintop removal mining, really big in the first decade. And of course, all the urbanization. You can see North Carolina killing it. The place that really kills is Texas. Wow. Houston, Dallas, Fort Worth, Austin. So then we take a sample and we throw the sample inside and outside of this mapped bare ground gain. And each of these pixels that are chosen, our sampling population's pixels, we can look at time series dynamics and Landsat thumbnails. We can get high-res data, say, oh, this is actually a coal mine. This is a conversion of, looks like forestry to energy, a power substation. And then we can say, okay, here's what the trend of these different dynamics is over time. You see like the global economic crisis. We're just kicking, going up very high with this dynamic, then tailing off after 2008. So it's really interesting because the total areas of this dynamic are less than Brazil's deforestation in a single year globally. So it's like a needle in a haystack. But you get very good precision with this method. So you're targeting this very tiny change dynamic, but telling a pretty good story. A bigger part of the story is like China is about a third of this dynamic. The US plus China is half of this dynamic. China's infrastructure is 7 times the US. We get that, right? We're not doing much in infrastructure. Look at these countries with the big red proportion. The red is resource extraction. So countries like Brazil, Russia, Australia, Canada, they're pumping oil, digging coal, digging iron for whom? China. So China can do all this stuff. So it's really an interesting thing. We're mapping, at scale, we're mapping bare ground gain, but we're getting some pretty cool, and my student Xingying showed that for commercial residential plus infrastructure, it's like a leading indicator. It has some correlation as an indicator of GDP change. So that's it. No, this is the general scheme. I'm going to go through some other schemes just to show you that it's applicable in different contexts. But I'll go down the hierarchy as I do so. This is Brazil. Yeah, another China. Well, it's not China, but Brazil's cropland is expanding. Most of it's for feedstock, soybean that goes to China, goes to Europe. And so in this map, we've got a baseline extent in green, and then we map the gain in blue, and we throw samples. And in these samples, we can start talking about, well, how much Amazon rainforest was converted to cropland? What are the dynamics in terms of time of that? Because they did put the policy in 2005, 6, 7 they have a soy moratorium where the big agro-industrials committed to not source soybean on newly deforested lands. So in this study, we can start looking at that. And we get all these great trends. So this is the sourcing of, this is new cropland on Amazon rainforest. And you can see the peak in 2004 and then boom, it gets really quiet. You can see the Cerrado's pretty high, but everywhere is pretty good. We can look at the cropland expansion and gain in terms of price of soybean. And if there's a good price for soybean, they grow more soybean. They extensify. The expansion of cropland is across the country. You see it everywhere, and you can see these numbers. It's great. The cropland area of Brazil doubles in 14 years, like 26 to almost 50 million hectares. Crazy, crazy. And if they do the whole Cerrado biome, they can triple our corn belt. I mean, they're going. I like this one. It's pretty anyway. In this picture, we see where cropland replaced tree cover by time. So before 2005, you have a lot of cropland going into the rainforest biome. This is the rainforest biome. After 2005, you see all these colors. This is the Cerrado. So the point is the soy moratorium is successful in stopping new cropland in the rainforest, but that doesn't mean demand dries up. Demand is high. and they go out to the Cerrado and they just blow up. There's no policy in the Cerrado. This is like Wild West. Just knock it out. Okay. Now we're going to do soy itself. So bare ground's easy. Cropland is okay. It's not super easy, but soy is hard. Soy is hard for a number of reasons. One is that you're dealing with all these other phenologies of crops, and soy versus corn versus cotton versus dry beans. It's hard. It's a very it's hard to discriminate. Then you also have different soy varieties, 90-day, 120-day. You have irrigated dry land. You have a good year, you have a bad year. This year in the U.S. is really hard to map. All the upper Midwest planted like a month later. What's your algorithm going to do with that? Very hard. So crops are really hard. Trees behave much more predictably. So we're trying to map soybean. And also the other thing tricky about this is we can't validate this from our desk. We cannot say with certainty when we look at any ancillary data at our desk that this pixel, this sample is soybean. So we have to go to the field. The way we do the field is we do a kind of cluster sampling. We do block sampling. So in this case, we've got a soy map going into the year, usually last year's soy. We convert that to a 20 kilometer by 20 kilometer block population. Then we put in thresholds, and your orange is weak in this screen. You see orange in that screen? You see yellow and yellow. But there's red. There's three strata here. We have highly concentrated soy, medium, and low. And we throw samples in each of those. So we have 25 sample blocks, 20 kilometers on a side for each of these strata, and we go to those blocks. And we just got done with this for all of South America. It's 2 months. It's like 5 teams. Each team is working for about 10 days. And we go to the field, and each block, we have a second stage sample that we go visit. So we have 20 points, 20 pixels that we have to visit in each of these blocks. And we record the stage, the condition, the height, obviously the crop type. And then we also grab training data, and we map each block. So we stack up Landsat and Sentinel-2. It's a bunch, all the growing season data, and we turn that into a map. I don't want to get too much into detail, but this map is really, really important. This becomes our reference data, and these samples become validation of that. And so each of these blocks is mapped. I like this slide because what it shows is that when we map soybean to stratify and target homogeneous populations of soy density, it's right. It works. We go out into the field. If we were driving down the road and say, what's the next block? It's like H20. Oh, it's a high block. You'll be getting there and you'll be like, 10 kilometers out, all of a sudden, ocean of soybean opens up. And so high, medium, low. When we use a regression estimator procedure, we have an auxiliary variable, the current year's soybean. We regress against these by stratum, and we get something like 350,000 square kilometers plus or minus 6,000 square kilometers. These are good numbers, and we do this for Argentina, Paraguay, Uruguay, Bolivia, Brazil, the U.S. We just added China last year. And the point of this method is that it's taking advantage of the satellite and saying we're applying the same method across all these geographies. This is an apples-to-apples comparison, very, very consistent. Brazil does not have a statistical method for doing their area. They call up cooperators and they report, and there's no uncertainty. I mean, it's just like it is what it is. Argentina borrows our statistical method with this area frame sampling, and they do have something comparable to our method. Bolivia, I don't even know what their approach is, but there you go. That's the idea. And then when we get that number, we can go back and make a final map of that number. So this is our final 2018-19 product, and now we're working on our 2019-2020 product. And then we've done it for 3 years. We're going to have 4 years now. We build an algorithm, a model. We run that backwards in time, and we describe the 20 years of soy expansion across South America. And you see it's everywhere. And what's interesting is it's mostly not in the Amazon. I mean, it's the conversion of a lot of pre-existing pasture lands, a lot of pasture conversion in Argentina. It's really interesting. 80% of the new soybean in Brazil is on pasture. They're not reducing their production of cattle either. They're intensifying. So it's really impressive. I mean, Brazil's intense. You can look at it by biome, no problem. So in general, this is our approach. We're going to do the U.S. again this year. We probably should add Canada. We got these 5 countries here, and then we've just added China. Okay. I'm going to show the first example of the planet data, and Josh is using planet, so he'll recognize this capability as, I think it's really cool. This is for Pakistan, and if you're in South Asia, East Asia, obviously Africa, but certainly South Asia, East Asia, it's intensified agriculture, but it's small field size, and Landsat has problems with that field size. So in this example, it's the same method. We have our sample blocks. I'm going to go into one. This is a very high-res image from Google Earth, and you can see a lot of detail here. This is what, in true color, this is what this looks like in Landsat. It's a bit of a problem. I'll turn it to false color infrared, so now all of the vegetation's red, and this is for winter wheat. So winter wheat is the key commodity crop in Pakistan. We work with the Crop Reporting Service there in Punjab province to do estimates. And I'm going to show you all of the Landsat images for the winter growing season. I think it's last year. Yeah, starting in 18 going through 2019. There are 15 images in the Landsat archive. You'll see the reds increases there. It gets a peak at the end of February. That's peak typically condition, and then it'll start to senesce. And you'll see this rust color come through. That's the senescence. The wheat is no longer growing, and that's our map. That's brutal. It's a brutal map. There are like 15 images. About 8 of them are usable, but that's what we can get. Now I'm going to show Planet, and again, Planet is 100 plus small sats, almost every 2 to 3 or 4 days at 3 meter. So this is the same time period for Planet. There are over 150 images of 57 unique dates. This kind of pisses me off. Sorry. It's like, come on. It's not the greatest calibration, but you overcome the calibration with a lot of data. I mean, it's just a lot of data. And you'll see, now we're getting, the senescence, it starts to senesce. You see a very clean brown down. And all that stuff that's vegetated is not wheat. That's pretty neat, I must say. So we can create composite images. These are 15-day composites from all those data, and we can build these phenologies. That's a wheat phenology. This is a real signal. This is a greenness index, NDVI, for this area. If I go through those composite, we also do field cuts the same way. We do go to the field in the same model. I just want to remember that. But here are the 8 time series composites, and then we have the map. So that's the Landsat map. That's the Planet map. And these data are great as reference, similar to the soybean. So for smallholder intensive ag, like you might have in the Northeast China Plain, the North China Plain, Southeast Asia, some of the rice cultivation, South Asia, I think this is just fantastic to use. Okay. Now I'll go to another biome, and the big land cover theme for climate change, and one of them is rainforest. And I'll tell some stories about our work in the rainforest. And a lot of our work here is not just getting the rates of change. We start with that, but it's really about the drivers. What are the land use outcomes that are driving change? What are the dynamics? How can we illuminate the stories in a way that kind of push either big funders or governments or protocols towards solutions? So what's the big driver? What's the biggest driver in the Amazon basin? Clearing? For deforestation? Pasture. How about here? If I can skip like 20 slides to give the right answers. Sorry? No. Logging is important in some countries, but it's not the big driver of forest loss. No. Subsistence farming. And here? Indonesia? It is palm, but it's really bizarre. It's actually just land grabbing, but palm is the thing that ends up going into those places. And so you have different responses for these different geographies, right? So we start off with just our typical approach where we do our sampling. We can see the success of Brazil. We can see Indonesia increasing. We can see Congo increasing. And Congo is pretty impressive because it's It's not mechanized, but it's still almost over half of what Indonesia does with mechanization. Fine, we can do that. But then we can also go to each geography and tell different stories. So this is just the sample-based approach to break out the loss into different components and show that pasture is the thing. Pasture is the biggest land use dynamic inside the rainforest. Soy is not. And when you talk about those fires this summer, it's ranchers. And when you talk about those, this is interesting. So you guys did pay, you heard about this. It's got huge coverage, right? What's interesting, my summary of that whole thing with Brazil and the rainforest and the fires last year is they got a bunch of it wrong, but the effect was good because it raised awareness and it caused some internal, I think, reflection by the Brazilian government. What's interesting is that the last 5 years have been really bad for fires, especially the El Nino 2015-16. Fires that year much worse than this past summer. Didn't make any media outlet. Why did we get this as news this year, not 2015-16? Why was this in the news? It's not as bad. There's 3 reasons. One is harder to explain than the others. Sorry? Smoke. Smoke went to Sao Paulo, and they were choking on it, and they were like, holy cow. And most of that smoke's from Bolivia. Bolivia had a horrible bad fire year. They had the guy who was just deposed let the lid off and said you could burn the forest for pasture clearing, and they did. And all that fire that's fire circulated over Sao Paulo. What second one?
Politics.
What? Politics. And who's the guy? Bolsonaro. Bolsonaro is the very hard right-wing rhetoric, way 10 times worse than Trump's rhetoric. Way. Pushing about, just paving over the Amazon. And that gets people's attention too when these fires happen. Another thing was that NASA and INPE, the Brazilian Space Agency, compared a particular month of fire to last year, and last year was a very low year, and they said it's 10 times greater. Cherry picking. Fine, whatever. It's true, but it's a bit tricky. So that really caught everybody's attention. The head of INPE got canned. He got fired by Bolsonaro because he insulted him. I mean, it wasn't strictly. I mean, he gave him a reason to fire him, basically, but it was not good for him. Anyway, so there you go. You have these fires going on. What's interesting about the fires, a lot of them are not in the rainforest, but also they're definitely not associated with cropland. So when you read the reports in the media, they said soybean and cattle. These are the 2 commodities that are associated with these fires. And the soybean farmers are like, what the hell are you talking about? Soybean, all of the row crop farmers want organic matter in their soils. If their field catches fire, they have mineral soil, they have to go back 5 years, 10 years to recreate that. If they're growing a second corn crop in the dry season, I was talking to the guy who runs a combine, he said, if that corn catches fire, well, that's obviously bad, but we could also blow up my combine. They hate fire, and you see that here. So when President Macron says we're going to boycott Brazilian soy, the big producers they lose their mind. They go to Bolsonaro, what are you doing? Egging on the fire and celebrating, celebrating the day of fire in Novo Progresso, which is like right here. So this is all cattle ranching. Soy doesn't want anything. I think that's a good outcome because it creates this, pushback to Bolsonaro and his like Wild West kind of approach to rhetoric on the Amazon. So interesting. A lot of the story mischaracterized. I have this in here just to show you that. I don't know why I put this in here, but we do near real-time alerts and a lot of the data I showed you are near real-time active fire. We have near real-time forest loss. So one of the challenges with this Brazil thing was we're trying to count. It's very strange. Scientists, we like to get our data, study it, polish it, iterate it. 3 years later, we might get a paper, And now we're like, oh, we've got these data. Let's push them out the door. It's nerve-wracking, right? But we do have near real-time alerts that we produce daily. They're summarized weekly by the Global Forest Watch, and they showed they showed in fact that a lot of the fires were not in the rainforest. They were on maintenance fires on pasture. Some places they were. Some of them were in the rainforest, but a lot of them were not. So no problems, that's the alerts. In Indonesia, I'm skipping over the Congo and Indonesia, come back to Congo. Same idea, we throw these samples and we build out a series, and this is amazing that when we look at these samples of rainforest loss in Indonesia, the number one outcome is nothing. There are 9 million hectares at the end of 2018 that are idle. And it takes an average of 8 years from the clearing to where you might get something like palm oil. So they sit on this land. They don't have to deforest for a long time if they just want to fill in their holes with palm oil. They also, Indonesia gets half the production per unit area that Malaysia does, so their management's garbage. They really don't have to deforest for 10 to 15 years. But this land banking idea, this grabbing of land is, it's obvious. It's a great insurance policy, and when palm gets to be a nice price and you get some finance, you put it in. I find that really disturbing that there's a ton of rainforest is just sitting there, and they maintain it. They don't let it grow back. And these forests are the most valuable for timber by far. The number of merchantable trees per unit area is highest in insular Southeast Asia compared to Africa and Latin America. And we had fires there too. So this is the big El Nino year, big fires, quiet, quiet, quiet. This year, big fires. And we're trying to give the government credit for this, huge backslide. So again, this idea that like, yeah, you do well for a couple of things, maybe Norway, supports some gives you some money from out of their fund, and then it blows up. Norway's fighting. Norway has $1 billion program in Indonesia. Norway gives money to slow deforestation because they have a conscience about their hydrocarbon sales. Okay, this is Central Africa, which is a whole other story altogether. There is no big agro-industry here, really. On the coast there is here, the Gulf of Guinea, but not so much. You can see where all the action is in terms of forest loss. It's in where? Who knows their Central African geography? Yeah, that's right. Democratic Republic of Congo, this one. So there are pushing 100 million people. Let's call it 90 million people in Democratic Republic of Congo. There's over 10 million in Kinshasa. There's not that many people in the other Congo, Gabon, Equatorial Guinea combined. So this is the big demographic challenge of Central Africa. And it's reflected in the land uses. It's amazing. So when we do this work, we start with this loss map. It's very much like the bare ground gain. We just map loss. And we throw samples inside and outside of loss. So there's the loss highlighted. Again, you see DRC, all with axes. It's not, chainsaw some. We do our sample interpretations, then we get a result for Central Africa. So these are our samples. We can say how much is rainforest, primary rainforest, how much is secondary forest, about even in the DRC. In the logging, in the low population areas, higher proportions of primary forest, because that's logging typically, Asian and European and Canadian companies doing selective logging of one type or another, more intensive or less, some FSC certified. When we look at the land use outcomes, this is a neat little map. I like this. This again, the samples are telling a very rich story where the big agro industry in palm oil, so the conversion of tree cover to another land use, we see agro industry on the coast, mainly of Cameroon. We go inland, we see these pink colors. This is all logging, so this is selective logging of high value timber. And then we cross the border into DRC, and it's all smallholder agriculture. So DRC is interesting. It's like 90 million people. The UN predicts that by 2050 it'll be 200 million people. By 2100 it'll be 380 million people. It'll be the 5th most populous country in the world. And if you extrapolate, and when we look at our forest loss versus population, it correlates. And if you spin that outward, the forest is gone. It's hard to get rid of that much forest, but it's gone by 2100 if you still have smallholder ag being the livelihood of people. And so this is really, when they talk about the forest land use transition in America, we were all, farmers, and we deforested the whole place, but then government came in and we industrialized, people moved to cities, they got higher wages. We gave certain pieces of land a break, steep slopes on clay soils. We reoriented our ag production in the Midwest. We started growing trees down here, except for on some of the sandy soils where we'd still do peanuts and the like. There's no forest land use transition there. They just hammer it, and the fallows get shorter and shorter. 20 years might be a good period. You get down to 4 or 5. No, it's just rough. So they have this, they have a dark humor there, but the previous dictator back, like 30-plus year dictator, Mobutu Sese Seko, he had 14 articles in the Constitution, very high aspirational things you could imagine of a Constitution. The people said, yeah, but he left off Article 15, Article 15, which was débrouillez-vous, which means you're on your own. And this is Article 15 from space. Man, it's 90 million people feeding themselves. There's no food aid. There's no energy, exports to import cheap food like rice or whatever. They literally go out and feed themselves every day, the majority of these tens of millions of people. And the trend is upward for the primary forest. Okay, this is Republic of Congo, and it's a special case because it is in the IPCC. You have big deforestation countries, Brazil, Indonesia, Democratic Republic of Congo. And again, Democratic Republic of Congo, just with axes, is about half of Indonesia, pretty impressive. But then you have these high forest, low deforestation countries that want to be in the game, and they need to be monitored as well. These are countries like Guyana, Suriname, Gabon, Republic of Congo. No deforestation, not worthy of mentioning. Logging and shifting cultivation. Very hard to get the areas right, very hard to get the emissions right. So I'm going to show you some of the challenges, and this again, I'm moving product for planet on this set of slides. We can map with Landsat wherever we see disturbance. So any of these red squares, these are 2.5 kilometer by 2.5 kilometer squares, and anytime it's red, we saw disturbance. And so we're going to include that in our strata. We're going to pick, I don't know what it is, 25 of these little squares. We're not going to the green. We're saying Landsat's good enough for that. We're not going to the green. And I'm going to show you what Landsat looks like over one of these sites. It's up in a concession. It's this one. This is CIB concession. It's a Forest Stewardship Council certified concession. And this is what Landsat looks like. These are the best images in true color for the logging going on in this place. You can see the logging road come in. This is the best image for when the logging is occurring. And you can see little highlights off the roads of logging. Not much. It's really ugly. Check it out. What happens after the logging, and they fell the trees and they drag them out on these skidder trails, the green vegetation just obscures that signal. It's gone. The only thing that persists are the roads. And if you go over time, this is what we map with Landsat. So it's an indicator product. We're super happy. Like I said, the whole time, all this stuff, we're using the satellite to indicate where things are happening. We're going to go visit to try and confirm what the real measurement is. So we throw a second stage sample here, and we look at planet. So the Landsat tells us we need to go here, or at least this needs to be in our population for sampling. And if we select it randomly, we need to go there. This is what planet looks like. And I'm not showing you all the images like with the Pakistan example, just a few interesting ones. Here is the initial highlight of the road coming in, building it out, seeing some logging now. That's beautiful. That's like money shot. 3-meter data, you see all of the extractions, really nice. And there's a couple like that. Check out afterwards. It cleans up. Gone. Just the roads. So Planet is really great because it's 3-meter. It sees the individual tree fellings, but it's high temporal. You get the maximum. You get the picture with the best contrast to actually track it. So when we throw the second stage sample, if any of our pixel samples throw over these patches, we're going there. How much? 5. Yeah, I'm good. I'm almost out. So again, it obscures it. This is what we map with Landsat. That's what we miss. That's brutal. But we go there and with these second stage samples, and the ones that are highlighted red overlap with the planet, and we fly a LiDAR. We do some paired science. We fly undisturbed pixels compared to the one that's disturbed, and we try to look at, we do some inventory. And this is very early stage stuff. We think this is the way that you track carbon inside high forest, low deforestation countries. You're not doing area at all. You're measuring structure, over paired, undisturbed, and non-disturbed forests, and you're getting at a kind of committed emission that way. Okay, just to wrap, I got one other example, sorry. So this is DRC again. This is a weird example, but here we're mapping settlements. This is all of the settlements in Congo. And then USAID does these health surveys, demographic health surveys, and they're probability-based stratified samples, and they do a lot of anthropometric measurements of health of folks, but also number of folks. So what we do is we stratify on this, and we throw samples, and we get into the samples, and we see how many structures, housing structures are in there, and they have a number in the health survey that says number of people per dwelling, and we can convert that settlement map into a population. And it's really kind of neat. It's just an academic exercise, but they've been extrapolating, you know, made-up numbers forever there. You know, to understand how many people are there. So we're getting 96 million. I think the number right now that they have is 80. And in the end, our thing is that we want to do this at a global scale, but we map global water dynamics like Morella. We've got all the pixels, Q8 as water, non-water. We can map tree cover high up in that hierarchy. We can map forest type in terms of natural, tall, dense, humid tropical forest. We can do a GIS analysis and just show where the biggest blocks of that are. We call those intact forest landscapes. We can differentiate terra firma from wetland, whether it's forest or grassland savannas. We can bring in the dynamic where the tree cover is being lost. We also do gain. I'm not showing that here. We can add where people are in terms of settlements. We can put in the agricultural footprint. This is the Swidden kind of rotational landscape of shifting cultivation. You know, we can add protected areas, what have you. And then we can put polygons around all the settlements and show that, you know, where dense, this is just to bring out where people are cheek to jowl compared to these last intact forests. So this is where we want to go with, you know, continental global data. Map all the land cover land use themes, get at the drivers, do some analysis on dynamics and say where the state of the planet is and where we're trending. Right now we're not trending in a very positive way, as you likely know. Very few success stories in terms of, you know, modifying our behavior in terms of land conversion. This is the same thing for a zoom in the Kwilu province. And what's cool about it is the closer you get to Kinshasa over here, the capital, just dense, less dense, wild. And there's no reason, there's no reason for that except that this is more connected to the city, and the fallows here are getting down to 4 or 5 years. Here they're like 10 to 15 years. Here they're 20 years. And it's just a really, just clean. It's just a clean, like a graphic of where the pressures are in this country. Okay, so I'm done. This is, I think that, you know, I would characterize, obviously, our current state as being the golden age of satellite data, because we do have these 2 Landsat instruments. Another one's coming online next year. There are 2 Sentinel-2A instruments. There's a radar instrument, Sentinel-1, that is freely available as well. So we've got this fantastic constellation. In terms of methods, you know, the algorithm knows nothing, so I really emphasize the fact that domain experts on the environment know what questions to ask, but also know how to iterate these algorithms and control them so that they bring out a product that's the best product possible. I don't think, you know, the deep learning machine learning engineer is going to make a great map. I don't think so. Rigor in mapping includes area estimation so that we follow proper procedures to give the best estimates to serve decision support systems like international protocols and the like. And then, you know, it's just kind of up to your imagination what questions to ask. It's super fun. I mean, you have so much data. I mean, I feel really badly for other disciplines that could pose the coolest hypothesis, but like, where are the data, right? Social science, that type of stuff. Sometimes it's there, sometimes it's not. But we just have, there's data pouring down over us right now from the space. It's just crazy. So it's like we're cheating, for sure. I think that's it. Thanks. How long did I go?
About an hour.
Sorry.
So we're at the hour mark.
Sorry.
Please ask, if you need to leave, go out of tradition, but if you want to stay for questions.
Sorry, I took my time. Sorry about that.
It was great talking, Matt. Thank you.
So questions
Yeah,
from
one.
So sometimes you also use the image with cloud to do the land cover map?
Clouds?
Yeah.
We want to throw away all the clouds. We have a QA model at the very beginning that looks at every pixel. It's not perfect. So our algorithm has to be tolerant of some contamination. It's very hard to map clouds,
Yeah.
but we do our best and usually have a very clean result. That's,
Yeah, you detect the cloud and then you cover everything.
we throw it out. We throw that pixel out. It's like it's missing data.
Yeah.
So an image might have 10% good data. We want the 10% good data. We throw the rest out. Most images have some clouds, especially in the tropics.
Yeah, yeah.
Yes.
And so y'all are pulling all this down and processing it yourself,
Right.
And you're getting that from Landsat, Modus. Are you getting everything you can, I guess?
I mean, it's really interesting. We have the entire Landsat archive. We have about 15 petabytes of storage. We're going up to 21 petabytes. It's a huge system. And if it were just Landsat, we would be cooking. We were so comfortable with Landsat. But now it's Sentinel-2, which is 10 meter, 20 meter, more bands. It is huge volume, and we haven't gotten comfortable with that at scale. Planet, we can't afford to buy at scale, but it's 3 meter daily. It's crazy. So the volumes, it's a great problem to have. But once we finally solved Landsat, then they keep dumping other stuff on us. And so I don't know how tenable our model is moving forward, but we do it in-house. We have a really great systems architect and a really great data processor that manage the whole thing and process it. But it's hard, especially looking forward.
So going forward, are you looking at moving your compute to the data rather than bringing the data to you?
Not yet. Not yet.
Not
Because the cost model, NASA, a bunch of folks are doing this. When you work over large areas, you're going to pay a lot of money for getting those data off of glacier, the glacial storage, or even the cycle. So like in Canada, Mike Wolder does annual forest disturbance mapping with Canada, and he says on Amazon Web Services that is going to cost him $128,000 a year. And he's like, if I use that for hardware, I can do it myself. So I don't think we couldn't, it'd be too much. And what's great is right now they have the Jedi instruments, the LiDAR on the space station, and we've used it to calibrate our Landsat, and we're making height maps. And we ran global algorithms 8 times in the last 2 weeks, just iterating this map on our own. And we don't have to talk to anybody. I mean, it's so great. If we were to go up there, we would hit paywall. We would run out of money very fast. And our systems architect's done it. He's like, we are much more affordable than Amazon Web Service, given our global scale.
I think you made a stratified sampling for each land cover type, right? And,
Right.
My question is, how do you ensure that each sample will not go into 2 different land cover types?
Oh,
What's
yeah.
the base?
Right. I mean, if it's a mixed pixel, we record that. If it's on a boundary, we record that. And for certain themes, there are a lot more mixed pixels than others. So if you're doing forest loss in Central Africa, there's a ton of mixed pixels. And the estimate can really move a lot if you don't pay attention to that. If you're doing soybean in Brazil, mixed pixels are not a problem. I mean, just...
What about the sample?
Oh.
Minimum mapping unit?
Oh, I'm sorry. Sample is our pixels, our 30-meter pixels themselves. So that's our population from which we infer the estimate.